I did my PhD in the University of Oxford in quantum computing. So we would go up and code a whole separate simulation, C, using Quest, this Oxford-developed simulator of quantum computers, another big one of my projects. Get the results. We get really lovely, plots or data for plots. And then we'd go back to Mathematica to visualize that data. So Mathematica was the start and end of our workflow. Mathematica, or Wolfram Language, is sort of like my primary tool for doing analytic or symbolic study. So often the mathematical origin of the algorithm I end up devising all comes from interaction with Wolfram Language, which could just be visualizing the way amplitudes are moving around in the quantum space, or be analytic calculations. I remember, for example, one of my general relativity courses, we had to calculate some metric tensor. Evaluating each element requires a huge analytic calculation, and very cruelly, most of them simplified to 0. The lecturer had sort of played a prank on us. So maybe like 2 of the 16 elements of the tensor are non-zero, but you couldn't establish that except through this absolutely horrible series of tensor algebra. But since he permitted use of tools, we could do it in Mathematica instantly. It didn't even require like custom functionality. We just expressed the tensors in Mathematica. I came away from the summer school, is still not mastering a language. I'm sure it takes a lifetime to master, but coming away with a whole new appreciation of it. It was no longer just a language to me. It was like, oh, it's this computational machine, and now I have a better understanding of how to interact with it.
Hello, everyone. We are here today with Tyson Jones. Tyson is the Innovator Award winner in 2023. And before we start this very nice interview, I would like to thank you very much, Tyson, for agreeing with this quick interview.
Oh, thanks for having me.
And we're going to discuss a lot about your Innovation Award, a lot about your work that you have been doing, especially using Wolfram Language. And to start with that, could you begin by telling us a little bit about your background and how you became involved in quantum computing at all?
Oh, sure. Well, yeah, I'm Tyson. I'm originally from Melbourne, Australia. I'm currently a senior maths library engineer at NVIDIA, where I develop scientific software for simulating quantum computers. These are the QQuantum libraries, if that term has been spreading. I have a maths, physics, computer science triple major from Monash University. And upon graduating and wanting to do a PhD, I didn't want to give up any of those topics of my majors. So quantum computing was the natural union of the 3. And I did my PhD in the University of Oxford in quantum computing. And then that I bounced around in postdoctoral positions between the UK, Zoe Holmes' EPFL group in Switzerland, Professor Kasuke Fuji's University of Osaka group, Quantum Motion London, a UK startup developing silicon-based quantum computers. That's not an advertisement for them. The UK National Quantum Computing Centre, and IBM Research UK. And in another life, I was interested in gravitational waves and quantum turbulence. But since my PhD, I just stick to quantum computers and how to classically emulate them. And some of my research resulted in the software projects Quest and QuESTlink, as I'm sure we'll speak about. The latter is primarily in the Wolfram language. And personally, in my spare time, I guess I write a lot of poetry and play instruments, and complain a lot about the superiority of Melbourne to every other city I've moved in.
What kind of instruments do you play?
Well, sensibly, I play well enough to claim I play them. Bass, guitar, and piano. But I've tried, to varying degrees of success, to learn the violin, the flute, and the melodeon on the little kalimba, which is easy enough. Everyone can play.
So which one do you play best, in your opinion?
Yeah, it's probably the piano. It's maybe not even well enough to call it best or good in any measure, but the piano is my favorite instrument, I'll say.
That's nice. That's nice. And thank you very much for sharing this other part, this hobby part of your life, because sometimes we tend to describe ourselves very professionally every time. And it's nice to have this version of you as well.
Oh, this is all the guys. Nobody who knows me would describe me as professional. This is just the guys I maintain.
I see. So talking specifically about your Wolfram Innovation Award in 2023, you won this together with Professor Simon Benjamin, right?
Mm-hmm.
Could you tell us a little bit about what that recognition meant to you and what specific word it was highlighting?
Ah. Well, the specific work being highlighted was QuESTlink. It's this open source software package for simulating quantum computers. Why that was kind of special, there are lots of existing numerical simulators, so they represent the quantum state with floating point numbers, represent them either as big vectors or there's all sorts of tricks. But at the end of the day, the simulation is performed by a GPU crunching numbers. Whereas Mathematica, though a Wolfram language, has facilities for that. It also has these incredible facilities for symbolic manipulation and analytic simplifications. And so QuESTlink was aimed at that layer. Let's have all these analytic facilities leveraged for the study of quantum computers. Yeah, and so it has visualization capabilities, lots of utility functions that perform chores that quantum computer scientists are doing daily, such as calculating matrices which describe quantum circuits or investigating different analytic mathematical properties of quantum states and even circuit drawing. And what it meant to me, I mean, I suppose it was a reflection that, that the tool had a wider utility outside of, say, just my research group. So I am in contact with a family or a few research groups that use the tool. It's just a nice layer above existing numerical tools. Say, for example, you're investigating something that doesn't require supercomputer level computation. You just need to maybe do a back of the envelope calculation. Then Wolfram Language is fantastic for that. And QuESTlink sort of bridges that to an interface that quantum computer scientists would find really natural. But yeah, I suppose the Wolfram Innovator Award was a reflection that it had possibly a wider impact, so that it might actually have utility outside of my little niche.
It's really nice. And QuESTlink was developed during your PhD, right?
That's right. Yeah.
And why did you choose to use Wolfram language for that?
So I was already using it, as was Simon. So our workflow sort of looked like this. We would maybe on paper or on a napkin devise a quantum algorithm or an idea for an algorithm. It wouldn't be immediately obvious whether say the algorithm worked or the resource costs. So we would code a small scale simulation directly in Mathematica, just using the existing like linear algebra primitives and matrix operations. We could test that maybe like 5 to 10 qubits, get some sort of analytic assurance there's something here. Then we need to move to like the 30 qubit regime, just a little bit bigger, but the quantum state has exponentiated in its Hilbert dimension or its inner workings. And that was sort of a regime where you cannot be analytic anymore. So the existing Mathematica toolbox doesn't permit you to hit that scale. So we would go up and code a whole separate simulation, C, using Quest, this Oxford-developed simulator of quantum computers, another big one of my projects. Get the results. We get really lovely, plots or data for plots. And then we'd go back to Mathematica to visualize that data. So Mathematica was the start and end of our workflow. And, Quest in C was in the middle. And that was a small inelegance. If we needed to change a hyperparameter of our simulation as revealed in a plot that we were doing, then we had to go and do that full loop again. And yeah, Simon one day walked in. So we were both going through this workflow. And Simon one day walked into my office. Maybe it was a Friday afternoon or something, and asked, could we just do this all in Mathematica? Could we invoke Quest directly from Mathematica or Wolfram language? I'm sorry that I'll be interchanging those. I probably said, maybe, principally. And so I spent that weekend playing with WSTP. That's cool.
Okay.
From Symbolic Transfer Protocol, which is a software layer to sit between the Wolfram kernels and your own process. So e.g. a C or C++ project. And yeah, we found we could dispatch commands straight from Wolfram language to C, which would then invoke this optimized GPU accelerated high performance simulator backend and bring the results back to Mathematica. So we never had to close our notebook. We could just do it all via dispatch. And that was like unlocking a productivity, gold mine for us. We can now do full simulations entirely within QuESTlink, even those which had become intractable for analytic study. So yeah, and I think Simon came back in the office on Monday and I said, yeah, I've done it. Now we can like totally dispatch to Quest directly from Wolfram language.
That's nice. And when you mentioned that you were thinking about an algorithm for making quantum computation, right? What was your goal at the time? What was the motivation to make a new algorithm like that? what kind of problem you're trying to solve?
Okay, so yeah, a lot of the early research of my PhD was in a field or studying a class of algorithms called variational quantum algorithms. Um, a quick little aside about the state of quantum computing. It's difficult experimentally. Today's quantum computers are very prototypical, experimental. They're very limited, noisy, inaccurate. And there was a big research effort to try to devise quantum algorithms specifically tailored to the imperfections of the current quantum computers. So that way we could actually make use of these prototypes rather than just telling, investors in experiments like, oh, wait 20 years. So variational algorithms, this class of quantum algorithm, was an exciting candidate for near future utility. So maybe these algorithms are compatible with imperfect quantum devices. And these algorithms do an optimization step. So there's lots of feedback going back and forth between the quantum and the classical machine. And a lot of the algorithm are based on calculus. Maybe we're doing a gradient descent, you could imagine. So that's sort of an area where, maybe I wouldn't say it's harder to verify, but there's some more mathematical nuance in checking the correctness of your algorithm because you need to be doing calculus to get the true. Let's say, well, it's not a perfect explanation, but anyway, it meant it was an area where one really wanted to play with symbolics in order to verify the quantum algorithm. It would be sort of a nuisance to use just numerical libraries to compare the output of your quantum algorithm to. And so, of course, Mathematica has, natural symbolic computations in calculating gradients. So there was a no-brainer to perform all that. So I think we devised a few quantum algorithms at the start of my PhD. Variational imaginary time, that might not mean anything, or variational Hamiltonian diagonalization and recompilation. These were candidates for near future quantum algorithms that might be compatible with quantum hardware that, I ostensibly studied with QuESTlink and Wolfram Language.
That's nice. If I understood correctly, you meant about when you have like a real quantum computing, you have like, for example, thermal fluctuations that can destroy entanglements, something like this. So I know that the idea to nowadays is you want to perturb as less as you can your qubits so that they do not lose entanglements, but at the same time you make the measurements. Is that correct?
Yeah, that's a very high level. Well, we have these like opposing tensions. So when we're not touching the qubits, we want them to do nothing. We don't want them to interact with the environment and decohere. We lose our entanglement, as you say. But then conversely, when we do touch the qubits, we want them to do exactly what we tell them, which sort of means our control hardware, needs to have this double property. It doesn't interact at all when we don't want it to, but when it does interact, it's extremely precise. The actual nuances are very platform specific. There's like, tens of candidate architectural designs of a quantum computer, and they all have different passive and active noise processes. It's a real circus. It's horrible. I sympathize with experimenters a lot.
And so your quantum algorithm in terms of QuESTlink, I mean, this is a very simplistic sentence that I'm going to say, but it incorporates these kinds of imperfections of the experiments of quantum hardware, as you mentioned, so that it becomes more close or closer to what one would have when making an actual quantum computation in a real quantum computer. Is that correct?
That's right. Yeah, we have sort of two modes you can simulate in that use the state vector and the density matrix formalism. And the state vector formalism can only model precise quantum states. These are quantum states that still have, superposition and entanglement, so they have uncertainties embedded in them, but they're all quantum uncertainties. Whereas the density matrix formalism, just this mathematical formalism, can factor in classical uncertainties. So maybe you're uncertain what your quantum computer actually did to the state. And Quest and QuESTlink have capabilities for simulating both of those. So indeed, you can use them for simulating idealized quantum computers of the future and for simulating imperfect quantum computers of today. Sometimes these techniques can be very expensive. They have exponential growth in the number of qubits. So
Yeah, that's what I'm going to ask. Like, what's the typical time scale to make a quantum computation? Depends on the number of qubits, I'm aware. Yeah. So, like for a few qubits, what would be like a typical time scale for a computation?
That's still very tricky to answer because, of course, that's a lot like asking, um, how long does a classical algorithm run? It's like, what? That depends what it does, Flipping a bit, that's pretty quick. But I will say, yeah, I'll say less than 10 qubits, I think is considered trivial for almost all applications one is looking at. So, okay, this is a dangerously broad statement, so I'm sure I'll be corrected in the future. But if one is looking at, say, 8 or fewer qubits, there are really no questions that we need to ask that would require computation slower than, like, I don't know, a minute.
I cannot help myself to ask about based on your expertise in the field of quantum computation, what do you think will be the future of quantum computation?
Ooh,
Because of course, a lot of people, what people would want is everybody to have their own personal quantum computer. But this is more like an utopia than a reality.
Right. Okay, yeah. So I can make some statements against that. So yeah, you and I will never own personal quantum computers for two reasons. One, they're just way more expensive and difficult to operate than the current classical counterparts, and that's because they require observing quantum phenomena. Quantum physics, is this weird new physics that takes over at very small and ultra cold scales. So there's nothing in this room that I'm aware of that is operating under the laws of quantum mechanics, or should I say that I couldn't sufficiently accurately model using classical physics. So if I wish to see quantum physics, I need to enter a laboratory, which is very expensive, and it prepares a quantum state, and that quantum state is very hard to keep alive. It's very, very fragile. So right now, it's looking like we need enormous amounts of refrigeration and control hardware to prepare the computational state. And, famous last words, maybe we could eventually scale that infrastructure to be small, but, we can't even handle thermal throttling issues in supercomputers today. My laptop thermally throttles, and it's been decades. And like quantum computers break at, a few Kelvin, yet alone room temperature, or yet alone boiling water scales. So there's really no hope that this infrastructure in front of me can reach quantum scales of temperature reliably. So that's the other thing. So that's the first thing, sorry. Very hard to just operate and control the device if it was in my house. Secondly, we don't need one. You and I aren't running, well, maybe in our research we do, but in our day-to-day lives, we're not really doing computations that have quantum advantage. Quantum computers are asymptotically exciting in that we have devised algorithms that have better scaling than classical algorithms, but for which each individual step is much slower. So like rendering a web page won't use quantum. Right? Polynomial time algorithms, classical algorithms, don't get any benefit from quantum. Trying to use a quantum computer for schemes for which we have sufficient classical techniques is pointless. It's more expensive and it slows everything down. So yeah, if you gave me a quantum computer today, I would use it in my research, which would be predominantly for building better quantum computers, but there is no problem in my personal life which I could possibly use. And even some applications which maybe are more convincing have pretty extreme pitfalls. One example is big optimizations. When I use Google Maps to navigate, to find the shortest path between different points of the New York Manhattan grid, an optimization algorithm is being run, and there are some works that suggest, well, maybe optimizations are candidates for quantum advantage, but these are like very, very contentious areas of quantum. So the applications of quantum computers that are the most promising or universally accepted as exciting and promising, I have no need for, nor you, in our personal lives so far. We won't be running quantum algorithms on personal quantum computers. So it's very much unlike the GPU. What's a more realistic picture? We will have big cloud infrastructures. So maybe, select computational entities will have a big quantum computer and we'll rent time on it to run scientific problems, or pharmaceutical industry giants will use it in their calculations. But yeah.
So getting your own personal computer is like getting a rocket to go to the supermarket.
I would say so, exactly, yeah. And the time you spend launching the rocket, the rocket's very, very fast, but the time you spend launching, like you could have walked back and forth.
Exactly.
Yeah, that's a great analogy.
Thank you very much. This was like a very nice answer because we all see some kind of news on that, and usually it's nice to talk to someone that has like a good expertise on the field to get realistic. And changing a little about the subject, as you mentioned in the beginning of our interview, you moved from academia to industry, right? And so how was that transition? Can you tell us a little bit about that?
Yes, I'm still transitioning, let me say. I moved over in September last year, so it's only been I don't know, less than 5 months. I will say I'm extraordinarily lucky because the work I do for NVIDIA is still primarily research in quantum computing. I'm no longer devising quantum algorithms. That's totally over. Hopefully that chapter of my life resumes one day, but not for now. Um, I'm just developing classical simulation techniques. So some of my time is spent with like implementation optimizations, like e.g., how can I make this established code or this established algorithm run particularly well on the latest NVIDIA hardware? Yeah, and maybe that's less academically exciting. It's more of just an engineer's job to fine tune. But those harder optimizations are the last things we seek. Right now, the kind of things we do are so novel in the literature that there's still huge algorithmic optimizations to explore and get to first. And they always have better benefits than the hardware optimizations. So the work I was doing in the last few of my postdocs, which is devising accelerated techniques for simulating quantum computers, it's the same work I do now at NVIDIA. Things change in that motivations for functions are expressed differently. In academia, for instance, somebody would email me and say, I want to use Quest or QuESTlink for this. It's slow at this particular part. Can you optimize it? Or there is a trick I'm missing. And then I might think, oh, actually, that primitive you're performing could be shortcutted with this method. Whereas our priorities for industry software, there's a much deeper, longer set of questions and priorities to answer to choose how to implement things. And the language is very different. So we talk of or language that is insufferable to an ideological academic. But the actual work I get to do daily is pretty much unchanged from what I was doing in academia. And I consider myself very lucky for that.
And are there some resemblances with the QuESTlink with what you do today in terms of, or only in terms of the optimization of the algorithm itself?
There's no resemblance in terms of the way that QuESTlink operates, but I do use QuESTlink like very extensively in what I currently do at NVIDIA. So I mentioned we develop algorithmic optimizations. The basis of these optimizations are often mathematical. So you go away and traditionally, I work either in a notepad in a cafe deriving things, or I'm sitting at my desk banging my head on the wall. And Mathematica or Wolfram Language is sort of like my primary tool for doing analytic or symbolic study. So often the mathematical origin of the algorithm I end up devising all comes from interaction with Wolfram Language, which could just be visualizing the way amplitudes are moving around in the quantum space, or be analytic calculations. I can give a very explicit example. One of the latest libraries we released is QPauli propagation, or QPauliprop, which is a simulator of quantum computers that uses the Pauli propagation formalism, which is just a particular basis of modeling the quantum system. And the mathematical primitives of that simulator are a lot more complicated than the state vector formalism, which is sort of the more natural formalism for quantum theorists to think of their quantum system. And each operation we implement for the simulator has a lot of mathematics behind it. And I could sit and just calculate each of these Pauli transfer matrices for the series of operations I wish to support. But with the right setup in Wolfram Language, I can compute them instantly. So I can instantly compute a matrix representation of a certain operation, and then I can look at that and go, oh, how could I implement that optimally? And then I can exploit sparsity or other properties I notice. But the very first step in my workflow for implementing a new operation into the simulator is to use Wolfram Language to study the mathematical properties of the operator in question.
Oh, that's nice. It's nice to know that even though you're still using those tools that you use in your PhD, I mean, Mathematica, the development of QuESTlink, and today, even at NVIDIA in your work there, you're still using that. This is really nice. Something that I would like to ask you is that you went to the summer school, right?
Yeah, that's right.
The Wolfram Summer School.
a lifetime ago, almost 9 or 10 years ago now, I think.
It's nice that you divide your life in many chapters. Like you have the gravitational waves one, and now you had the Wolfram Summer School one. So how was this experience?
Oh, it was amazing. Yeah, if I can I can turn this into an advertisement for the Wolfram Summer School. It was absolutely fantastic. Um, Firstly, just for really understanding the Wolfram language. So I was using already Wolfram language extensively through my undergraduate. I think I was introduced by one of my physics lecturers. It might have been Russell Anderson, um, who's now also involved in quantum computing. And maybe he was just showing us how to do certain calculations analytically and mathematically much faster. I remember, for example, one of my general relativity courses, we had to calculate some metric tensor. Evaluating each element requires a huge analytic calculation, and very cruelly, most of them simplified to 0. The lecturer had sort of played a prank on us. So maybe like 2 of the 16 elements of the tensor are non-zero. But you couldn't establish that except through this absolutely horrible series of tensor algebra. But since he permitted use of tools, we could do it in Mathematica instantly. It didn't even require like custom functionality. We just expressed the tensors in Mathematica. So I was already using Mathematica / Wolfram language extensively. And then, and I thought I knew the language very well. Every once in a while, I'd be tricked by maybe some unintuitive syntax. But attending the Wolfram Summer School made me realize I didn't understand the language at all, that it's in fact much more powerful and interesting paradigm than I first appreciated. I mean, it's like a Frankenstein's monster of a language. It's functional, it as well has imperative and declarative elements. And I came away from the summer school, it's still not mastering a language. I'm sure it takes a lifetime to master, but coming away with a whole new appreciation of it. It was no longer just a language to me. It was like, oh, it's this computational machine, and now I have a better understanding of how to interact with it. That was one thing, just the benefit to the language. Two, and there's a research benefit because you're surrounded by very like ambitious or you're surrounded by other kids essentially who are also fascinated by research questions. I mean, kids ostensibly or adults. So it's just really charming to be connected to a research community like that, and you get to have one-on-one interactions with Wolfram who would just look over your projects or give you projects that are fascinating, and it's kind of mesmerizing to see how much progress people can make on what sound like really ambitious research projects over a couple of weeks. Like how quickly the investigative process is accelerated with Mathematica.
Yeah.
But maybe the biggest takeaway from the summer school for me was Stephen Wolfram's himself. He's like very infectious ideology on computation. I'm going to paraphrase the lesson that I took away. So maybe I'm misrepresenting him and he'll begrudge me for it. But he expressed or interpreted this attitude that there's kind of a disconnect between computer science as an academic discipline and computational tools accessible to scientists. Academics in computer science create all these amazing algorithms, and maybe they get speed ups of certain kinds in certain settings, and they publish all this material and say, look, the scientists can use this and revolutionize these pockets of science. But the scientists who are supposed to use this stuff don't have the technical prowess or the computer science knowledge to implement these new algorithms themselves. Often they have deadlines for results, so they're just going to implement something dumb that they can implement quickly and wait several months to complete, rather than spend a year to understand a certain algorithm that completes in a day. And that was sort of a big shame. And Wolfram had this vision, if I understood him correctly, of bridging that gap with Wolfram language, having a language that has all these advanced algorithms just as like a really high level API or some sort of interface that lets you stitch these functions, which are in turn computing very advanced things, but have it so high level that a scientist who has no computer science knowledge whatsoever can rapidly use it for their application. And I became like enamored with that vision. I thought that was like a democratization of computer science. So even like, the unwashed scientists can be invoking subroutines and algorithms that are super advanced behind the scenes. And I think he infected me with this vision of the future where every computational primitive is an existing function inbuilt into the language, where you don't have to implement anything again. No reinvention of the wheel. You use existing things that have been invented. And so, I mean, correct me if I'm wrong, but now there are like tens of thousands of inbuilt functions, or at least several thousands.
Yeah. And also there is the repository of packlets. I think we talked about that, right? So that I'm not sure if the QuESTlink is one of those repositories. but there are a lot of user-created packlets that people upload there, and then you can extend what's already have in Mathematica with those packlets.
Yeah. Well, yeah, I'm not sure if I ever organized QuESTlink as a packlet because I was experimenting with doing things like connecting to a remote supercomputer during the use of QuESTlink, things that were hard for me to like package into a box for the packlet server. But yeah, I loved the attempted democratization, or let me say, I love Stephen's vision of what computation could be as a tool. So now I guess it's informed all the APIs I've designed since are as painfully high level as they can. I want them as usable. I want every computation. I want I love interoperability, but I don't want the user to have to pull things apart. I want them to have everything they need at an extremely high usable level.
Yeah, it's really nice, as you mentioned, like when you have like a built-in function that you just type in. Sometimes there's a huge code behind of that to make that work. That if you have someone like doesn't have like the special training or deep knowledge on computational science, they wouldn't be able to do that. But the built-in function is that way. And what was your project about during the summer school?
I had two projects, I think. The first was we were going to use machine learning to predict eigenstates of different quantum systems. So here's some random quantum speech. We have this operator called the Hamiltonian, which is a mathematical description of all possible dynamics of a system, say, or at least you could obtain all future dynamics of a system based on the Hamiltonian description and its current state. So it's like this very important object to defining a system. Okay, so the Hamiltonian, like all operators, can be diagonalized, split up into these constituents, whatever that means. And those are really important in several sciences for predicting behaviors. But they're very expensive. Diagonalizing a quantum operator is just a very expensive mathematical process. And so it's very slow. And we were wondering, could we train machine learning? Could we use machine learning to predict the spectrum or the eigenstate? So rather than doing this precise diagonalization, we get an approximate diagonalization fed out of AI. And then maybe we feed that into an iterative process that can improve it, or maybe we just use that in some applications. That was my first project, but confessedly, I made terrible progress upon it. The machine learning facilities of Wolfram Language were still in their infancy. Although I'm not blaming the state of development, but it required more expertise in machine learning than I had. So then I forked it into another project, which was developing tools for simulating and visualizing quantum processes directly. So maybe it was an embarrassing infantile project overall, which is using Mathematica to do 2D and 3D simulations of quantum wave functions evolving and plot them as prettily as possible. It was sort of more a pedagogical exercise in quantum theory, but interesting enough to be worth doing, I thought.
That's nice. And as a final question to you, as quantum technologies mature, what role do you think that Wolfram Mathematica and the broader Wolfram ecosystem can play in shaping the next generation of quantum research and engineering?
Well, I mean, I personally think Wolfram Language will stay relevant in all fields of physics and maybe lots of more research beyond that. Simply because it offers the lowest level of design and strategizing, which is playing with symbolics. There's just so much infrastructure for maths, for just core maths. And that's always relevant. Everything built in the sciences begins with maths. Do I think there's a specific role for Wolfram Language in quantum computing applications? That's super interesting. We don't yet even know what the full stack of software involved in quantum computation will be. For instance, the quantum computer is going to evaluate a quantum circuit, but preparation of that circuit to solve a certain problem is its own task. Optimization of that circuit to improve its resource costs or its error tolerance is another task. All these layers right now, we sort of just flesh out as we go and make open source repos, or some companies step in to produce them. It's not really clear what the right paradigm or platform is for many of those things. But I do all my circuit recompilation manipulations in Mathematica, in Wolfram Language, using QuESTlink. So I find it pretty handy in that regard. It's fantastic, like symbolic, manipulations of sequences. What role could it play in general? That's a fascinating question. That's a question for the Wolfram team. Yeah, I do, guys. I'm not sufficiently creative to insert it, but it certainly has a role in the research. I also want to speak against the idea that if we have quantum computers of a certain size and fidelity, we won't need the simulators or mathematical tools at the bottom like QuESTlink Mathematica anymore. That's simply not true. We could build CPUs today, and yet we still simulate them. Simulation can answer questions that either can't be accessed experimentally or are otherwise a nuisance to experimentally answer. So the simulation infrastructure currently, I mean, a lot of it might become redundant, but the act of simulation will always be relevant to quantum computers long after we have big fault tolerant, advantageous quantum computers.
It's nice. So thank you very much, Tyson, for sharing your experience with Wolfram Language and quantum computing simulation. I really enjoyed our conversation here. I learned a lot from you today, and just want to say thank you for agreeing to be here.
Yeah, thanks very much. Thanks for listening through all my unhinged ranting.